Okay, so I've been working on the Diviner team with my advisor David Page and with Bruce Bills, who's at JPL, and some of the orbital mechanics behind this story. So we're going to look at the history of the moon as a function of the obliquities it's gone through. And this is actually a really important part of this whole history of ice on the moon that we rarely hear about. The moon has not always been a good environment for collecting ice. During this Cassini state transition, which we've heard a couple people talk about this week, the moon got to very high obliquities, probably 77 degrees is the normal predicted value. And so we wouldn't have had cold traps at the lunar poles. And so this is looking at some of the objectives of what might have happened since that time. So first, what we want to do is look at how the lunar orbit evolved. Then we'll want to look at how this affected temperatures, all right? Because ice stability is exponentially related to temperatures. Temperatures end up controlling the situation almost entirely. Then we want to look at how that would affect this volatile stability, and does this explain the distribution we get of ice on the moon? And just no bias to anything, but this was just out of laziness. This was the one that Rick Elphick provided me, the lunar prospector neutron spectrometers, but this can equally be compared to what we are observing from LEND as well. And what we can see is this obviously doesn't really match the current temperatures we measure on the moon. Okay? That the distribution of ice that we see is biased well towards Cabeus, which is cold, but there's not things that are especially setting it out from the other cold traps in the modern lunar environment. So the question is, does the past lunar environment provide us anything different? Okay, so what would the past lunar environment look like? Well, we have to look at these orbital mechanics things, and I'm going to break it down into these two angles. The obliquity of the moon, so its tilt from its orbital plane, which is currently about 6.7 degrees, and the inclination of lunar orbit, which is 5.2 degrees. These come to the 1.5 degrees that we always talk about the moon being tilted. So what happened with the inclination of the moon? Well, you have torques from the oblate figure of the Earth, which was more oblate early on because the moon or the Earth was spinning faster, and then you have torques from the sun, which would like so the Earth would like the moon to be precessing about the equatorial plane of the Earth, and the sun would like it to be precessing about the ecliptic plane. And so that as the moon has moved outward over time, those forces have changed and caused us to go from a very large oscillation between those two planes to now being dominated by the solar torques, because we're far enough away from, or the moon is far enough away from the Earth that it looks like a point mass, and so it doesn't really have any torque on the moon in that way anymore. Then we go to this other complicated story of what happened with the obliquity history. All right, and I could go into a great deal of depth about this, but this is something called the Cassini state. And the main thing I want you to take away is that due to damping within the moon is always driven to precess, its spin pole precession will precess at the same rate as the orbital plane will precess. Right? We know this because the orbital plane precesses every 18.5 years, and so the spin pole of the moon also has to precess every 18.5 years, or we'd see the backside of the moon, right? And what that basically comes down to is these two it's actually the angular periods, not the angular rates as I write here, have to match in order for the moon to be in this Cassini state. And dissipation in the moon will always drive it into this state. So this here depends on how far you are away from the moon, or how far you are away from the Earth. But the spin precession of the moon itself really depends on the moments of inertia of the moon and its obliquity. So what I want you to take home is that as the moon moved away, the only way that you could stay in a Cassini state was by changing the obliquity of the moon, okay? Because you can't really change the moments of inertia as easily. And I'll thank Jennifer Meyer for probably discussing this in better detail earlier this week. Okay, and so here's what we get from our modeling of when this lunar obliquity transition happened. When we include a little bit of a hydrostatic moon, we have this happening earlier than had been predicted by Ward in 1977, but we're getting a little better. So we could put these things together and get the actual history of the tilt of the moon. And so this is what ice cares about on the moon, right? We have this 1.5 degree angle. So that means any crater wall near the poles that's higher than 1.5 degrees is going to really be shadowing ice. But that wasn't always the case. And so what we're going to do is look through some of the temperature consequences of these past tilts of the moon. And so we can see this is our map today, all right? And this is validated with diviner data. These are our diviner thermal models. This is just a map of average temperatures of the moon. And so we have lots of areas that are below, well below 100 Kelvin on average, right? And they can maintain ice. We go back to past obliquities, right, to higher tilts, and we can see those areas start to shrink. Some of them start to shrink even more. By the time you're tilted like 12 degrees, a lot of the things we think of as classic cold traps have disappeared, right? So this might really not be that long ago. It's, depending on the very unknown recession rate of the lunar orbit, it's between 1.5 billion and maybe 3 billion years that we've had cold traps. And before that time, we couldn't have collected ice. So that might be a very easy answer for why we have more ice on Mercury than on the moon, is that we just had a longer time to collect ice there. But let's think about the other things that control collection of ice. And a good simple model for this was put out by Shorthofer and Taylor in 2007. First of all, you need to think about the supply rate of the ice and then how the moon could actually collect that ice, whether it would diffuse downward into the ground by thermal processes. And so what we can look at is the supply rate and a destruction rate that they put in there. So that's like Lyman alpha light, cosmic rays, these sort of things that would eat away at molecules that land on the surface. And they got this distribution for what the supply would really be like. Okay, so, and then they also said, all right, how will that ice then diffuse into the ground, right? The diffusion rate into the subsurface is going to depend on your temperature. The warmer you are, the more mobile molecules are, and they'll be able to go down. So what this ends up leading is both on the hot end, right, where your surface density is going to be lowered because water molecules don't stick around long enough, you get a depletion. But on the cold end, you also get a depletion in how much ice you're going to get in the lunar surface and into the subsurface. Because if you're colder than, let's say, 90 Kelvin, the only way you're really going to get ice buried is by impact gardening, like Dana Hurley has looked at, or by, I guess, by a near impact that might throw some new stuff onto you. But the quick processes of thermal burial that could really protect you from some of the cosmic rays and other things are only going to happen when you're hotter than that. So what this ends up leading is this sort of hot spot where you have the ideal temperature range at which you could actually bury lunar ice and preserve it. And so what I had done was just use that simple model and look back with our lunar orbit history and seeing where you could develop ice in the ground over time. You can see the current moon is actually a really crappy cold trap, okay? I mean, it's a good cold trap, but it's not a good ice trap, right? And they're very different things, right? So places like Cabeus could collect surface ice, but other than impact burial, the thermal processes aren't there to actually provide you a way to get under the ground and be safe. Then we can go back to past obliquities. It doesn't look all that different at 4. At 8, we start to get this. And this is sort of interesting in what we heard from Bill Boynton earlier about all the neutron data sets are sort of showing an enhancement as you get closer to the poles in neutron, or in the neutron flux decreasing. So maybe past obliquities can start to explain that story. And then when we get to these higher obliquities, we actually get to start some of these cold traps become in the range of temperatures where they would be really good ice traps. So I can imagine if you had a higher flux of supply back then, you could imagine getting ice built up in these areas that we see today. And you can go back far enough where none of these places would have been good ice collectors because it would just be too warm. So we could put that all together with the Shorthofer and Taylor model, and we can, by weighting the supply history, saying, okay, we had a higher supply rate in the past, we can get something that matches the distributions we see, right? That biases the right place. But the problem with this model is that it's about 1,000 times too little ice to really explain what we see in the neutron data. And that's because the Shorthofer and Taylor model assumed a constant temperature, which isn't really a good way to think about how ice would be delivered into the subsurface. So that's what I want to look at a little more now, is how does ice actually get moved around by thermal waves? So this is just a picture we're always used to looking at for diviner sort of plots, but this is the average, this is the surface temperature is varying here, and then you get the, that will die off exponentially with depth. So this would be the maximum yearly temperature and the minimum yearly temperature with depth at a given spot. And so ice will be driven downward along a thermal gradient. The thermal gradient causes a vapor density gradient, and so a water molecule will travel along that vapor density gradient and be driven towards a colder spot, right? So it's sort of like the same thinking we have about cold traps, but with depth as well. And your supply rate will determine how deep that ice gets, right? So here we have, depending on how much ice you're supplying, that will determine how deep it was. And that's sort of what we went into in our 2010 science paper. And so if you're too hot, you get in this situation where that depth of that ice table becomes really low, either because just your temperature, you don't reach that frost point temperature to very deep depths, or just the fact that, like the supply model we saw from the Shorthofer and Taylor model, you just don't get molecules sticking on the surface when you're hot. The other end is the cold area, and here's what I was saying here, is if you're too cold, you're just going to have an ice table right at the surface. And those water molecules aren't going to get down unless you bury them by some other process. So they don't really migrate as quickly as they could thermally to really protect themselves from, just getting under the top few centimeters is all we need to get there. And so what this all comes to is that there's an optimum temperature and temperature amplitude space for collecting ice. Right, so you can imagine this parameter of moon stickiness, of how much a water molecule is going to stick in the subsurface based on your average temperature and your temperature amplitude. And so I've been doing some modeling now of doing full vapor diffusion models at different temperatures and different temperature amplitudes. And you can see I can get concentrations that are factors of 3 higher than what we got with the Shorthofer and Taylor model. So I'm now trying to apply these same sort of things. So here you see, this is an example of if you had a 50K amplitude variation on the surface temperature, which might happen in some locations, that will get too hot at times, right? And so you get biased towards the colder temperatures, right? But, and you can still collect ice that landed at the colder temperatures because you have these hot periods where you can pump it down. So these pumping models might explain how we can get enough ice. And so now it's trying to compare the history of what would happen at these given locations to the actual concentrations of ice we see. So thank you very much, and let me know if you have questions.
Thank you, Matt. Are there any questions? Bill Boynton in the back.
That's really some excellent ideas. That makes a lot of sense, and I guess I can see where, I mean, it's obvious after you explain it that temperature cycling is a good mechanism to move things around rather than just lock it in place. And I also like your idea of, for that, what I call the background increase in hydrogen towards the pole that's not really associated with any topography. Your mechanism might help that as well. So I'm very pleased you may be onto something, so thank you.
It's basically applying the same models that work for your Mars
to the
moon. It pays off. Yeah, homework.
Hey, great talk, Matt. How does your model, which is perfect resolution, so to speak, because it's a model, compare to the Lend hydrogen, where in Highworth there's cold temperatures but no apparent hydrogen? Shoemaker there is, Cabeus there is. At the blurred LP data, it looks pretty good. Will you get those kinds of conditions where the diurnal swing or that amplitude is different for each of those individual craters, and then can that explain why you can have that kind of diversity?
Hopefully, but I haven't done it yet, I guess is
Okay.
what I'll say on that. So,
Okay.
yeah, I mean, as you saw, using the simple models that I have done, you don't get nearly enough ice concentration to even start comparing it to the actual data.
Okay.
You can sort of get a qualitative distribution. But
You haven't yet
don't
looked
think I
at the
answered
differences from crater to crater in terms of amplitude and mean temperature yet?
But it has potential to see.
Yeah,
That's
okay,
the thing.
great.
So better topography models give us better temperature models, gives us higher.
And real data to verify the temperature models? Yeah, it's all good. All right, thank you.